So yes, indeed, it's nowadays quantum has become a bit of a buzzword, but actually, it's quantum physics is really old. Is more than 100 years old. Max Planck in the late 19th century started looking at sunlight, and he needed quantum physics to explain what the spectrum looks like. And also that it's what got the photoelectric effect is what got Einstein his Nobel Prize in 1905, and is the same effect that allows you to capture the images in digital cameras today. So the technology is really old. However, the buzzword is more related to quantum computers, which are not yet available. There are many companies trying to build them, but of course they're proving themselves very challenging to develop. I worked on such technologies maybe 20 years ago, so yes, I think they've come a long way, but we're not there yet, and definitely Rawsie does not use any quantum computing. However, quantum physics is a lot larger than that, and we use many concepts and practical equipment which is derived from quantum physics. So one of the big differences is that quantum physics is the only physical theory which deals with randomness. So most physical theories are in principle exact, and whatever you don't know or can't measure is a limit of your equipment. So, like if we were in a completely classical world, the better your camera becomes, just the better your image looks, and there's no limit in how precise that measurement of light is. Whereas what quantum physics deals with, it tells you exactly how accurate your best measurement of light can be, and exactly how noisy that pixel will look in your final image. So in Rawsie, there are three elements that come from quantum physics. So one is the technology behind Rawsie, the way it works is that it has a very accurate estimation of the noise that is present in each pixel. So that comes from some calculations that we've done for random number generators using optical sensors. The second part is the characterization. So the way that you calibrate cameras very, very accurately, you need to, like the way we do it for Rawsie, we need to be accurate within, say, 1 photon over the whole dynamic range of the camera. And so some of the equipment and techniques that we use to achieve that accuracy are derived from the quantum research labs where we used to work. And the third aspect is that quantum mechanics deals with information, and what we can do is we can characterize the loss of information that happens in the file using the mathematics and tools that we developed in quantum communications. So in quantum communications, what you do is that you send some photons from a source that can be a laser or a single photon emitter down a fiber to a light detector, and then you characterize how much loss have I had into that fiber, how much information have I lost from that light, and what so the actual model that describes is exactly the same model. Say, for example, if you have a light emitter and then you have your camera sensor, and you save your data from the sensor to the file. Now you can compare how much information did I really have within the light in the beginning with respect to how much information I saved in my compressed file. And so to have some very accurate measure of that so that you can bound your maximum acceptable loss, then it's very important when you define the target for your compression. And so that's also, that's the third element that we use in Rawsie. But yeah, to be clear, like we don't have any quantum computers or quantum processors. I think we would be probably doing something else if we had.